I am Nicola Durante from Engineering, and I'm presenting the Awareness and Comprehension Framework and Cyber-Physical Human Enriched Decision Support System. ATLANTIS aims to enhance the resilience and security of key EU critical infrastructures against natural hazards and cyber-physical threats. It involves 39 European partners and focuses on systemic resilience, adaptable security measures, and cooperation among stakeholders. The ACF aims to enhance the awareness and understanding of critical infrastructure threats, both short-term and systemic, through advanced computational methods. DSS analyses data from SAFER and other tools to detect risks in critical infrastructures, assesses threats, and decides on preventive actions. The ACF ensures privacy, analyzes diverse data for threat understanding, facilitates information sharing among CIS, uses ML for precise threat assessment, and ensures confidentiality compliance. DSS enables proactive risk management by analyzing current situations, identifying potential incidents, and facilitating preventive actions. It enhances situational awareness and collaboration among critical infrastructure entities, supports informed decision-making, and prioritizes risk reduction measures. On today's agenda, I will introduce, present the objectives, and show the inputs and results of the Awareness and Comprehension Framework and Cyber-Physical Human Enriched Decision Support System. The ACF and DSS leverage the data coming from the real world and processed by the detection layer. Their goals are to identify systemic threats and risks, to understand the scope and scale of incidents, to suggest preventive actions if needed, to forward the results to higher-level components. Core principles of ACF and DSS. The ACF and DSS follow Ensley's situation awareness theory. When someone meets a dangerous situation, he needs an appropriate and a precise decision-making process, which include pattern recognition and matching and formation of sophisticated schemes that aids correct decision-making. Technical details. The ACF, developed in Task 3.3, receives data from the detection layer in IDMEF format and using a complex event engine and ML components creates the situational awareness data model. The DSS, developed in Task 3.4, extends the situational awareness data model assessing the possible wider scope and scale of threats and can suggest mitigation actions. The demo scenario presented today focuses on the LSP-1 cross-border resilience in Italy and Slovenia. The scenario involves the rail transport of hazardous waste on the route between Italy and Slovenia, along the Villa Opicina corridor near Trieste. The CI operators involved are the Italian Rail Transport Operator, FST, Slovenian Rail Transport Operator, SZ, and the Italian Railway Police Operator, MDI. The threats, hazards, vulnerabilities and risks considered are safety risks, the compromised tracking systems and disappearance of the freight convoy. Traffic disruption, slowing down rail traffic for safety reasons can disrupt the entire rail network along the Villa Opicina corridor and neighboring routes. Environmental risk, as the convoy is transporting hazardous goods, it poses relevant questions about potential threats to the environment in terms of pollution. Public order disturbance, the slowing down of traffic due to safety concerns can lead to passenger frustration and public order disturbances. Organizational threats, slow communication across organization, lack of cross-organizational information sharing. SAFER collecting the data from its data sources is able to monitor the train 1824 from Ljubljana to Trieste. The current situational picture status, shown on top, is normal, with very low severity. The events are collected and shown as they are detected by the detection layer. We can see that the train 1824 has stopped updating its location and the severity and status of the situational picture have been updated accordingly. The SAFER high-level events are shown separately. The public disturbance alerts near Villa Opicina, detected by HIVIC, are collected and shown. The spillage of dangerous goods is identified as a high-level safer event as the sniffer sensor data coming from CEA detector is received. The possible affected leakage area is shown on map. The situational picture displays high severity and a critical status. The missing train is found and diverted. At the same time, however, a DDoS cyber attack on FST premises is identified by the indicators of compromise. As the attack is managed by the response teams, the severity of the situational picture becomes very low and the status becomes managed. CI operators will be able to review the specific incident in a separate dashboard. Using SAFER, the slow communication across organization and the lack of cross-organizational information sharing is tackled efficiently.